really not a fan of being taped. And so if everybody had been here, we wouldn't be necessarily taping unless somebody said, oh, that's good for me to review it. Okay. Today is the 17th. The next time we meet, I believe, is July 1st. Is that what you have on your calendar? At which time we're going to have an exam. So test 1 will be on July 1st. And cover the first 2 chapters. So it covers chapter 1 and chapter 2 of our text in terms of what we've covered. That will correspond to videos 1, which, if you remember, 1 had to do with proving techniques. So really that's kind of background. I mean, there was some set theory. It's come back here in chapter 2. But we have done 16 videos. That's how many you've been up. Okay? That's how many I've done. Today I'm going to do the 17th one, and I think it will conclude the chapter. And so I'm going to say 17 or 18. But I think I will conclude it today with video 17. So I'll do that after this class. Hopefully it'll be posted at the end of the day. So that gives us a good many days before our first exam, in some sense. And in another sense, you might be thinking, well, it's not that many days. I'd like to tell you that a study guide will be given to you, or will be sent out to you for test 1 by Sunday evening, this Sunday. I had mentioned last time about the exams, about my exams for this level of class or type of class, and they all have the same thing. I'm going to ask you to state some definitions. Okay, so it is a purely, what does this word mean? Not the idea, the actual words that describe what that particular term I'm giving you is. So it's the memorization of those definitions. I will tell you which definitions we've had. Okay? And pretty much all of them, or close to all of them, will be fair game. And that's a lot of them. For me, and one of your classmates came to visit me not that long ago and said something about, I don't know that I'm following the videos very well because I don't know the definitions. And my response to that student was, yes, without the definitions, we can't really progress. And so it's, for this particular type of class, it's vital. And even if we can quote the definitions, doesn't mean that we have a great understanding. It gives us a blueprint of what needs to be done in proofs, in some sense. It's verifiable characteristics for a quantity. You want to know if a person scored a touchdown, that ball had to cross the line, or they have to have possession of the ball within the plane, the goal, within the end zone. Does that make sense? So there's a rule, what makes something what it is. And that's definitions for us. So if we don't know the rules, we can't really progress logically. Okay, so that's something that I'm kind of big on. The second types of questions are usually named theorems. We don't have too many named theorems here, so that won't be a big part of this test. And then I will narrow down some things that I would like for you to be able to prove, and narrow down some example types that you should expect on the test. Okay? So that's what the test will be like, and I'll hand out that, or not hand out, but send that study guide to you on Sunday. So it'll give you some time to prepare for that. We have a homework 2. So these are just some things I wanted to start today off with, some announcements. Homework 2, if you remember, is due on, it's due on July the 23rd.
June.
Yeah.
Although I take
I think that is a Monday. Today is Tuesday. So that's Monday. Okay, next week. I had asked last time, do you guys have the capabilities of getting it to me, either coming to class, coming to the university, maybe sliding it under my door, emailing it to me in some electronic form. That's fine too. Okay? However you can get it to me. And if you have difficulty, you let me know. We'll make arrangements. The other announcement that I had, so the first announcement, second announcement. The third announcement was from Mrs. Thacker, our department secretary, and I think she had told some of you that she would be here till 6 o'clock today, and she asked that I tell the class, just in case you needed her, this is the math department secretary, Mrs. Thacker will be on campus. She had a change until 5:30 today. So those are the announcements that I wanted to start class with. I have graded your homeworks, homework 1, and overall they were okay. The score was there. It's out of 32 points. There was a high score, I think it was 31.5. So sometimes I get a little picky. Sometimes I'm even wrong. Imagine that. In grading. And I think so that was the highest score, and the lowest score was in the teens somewhere. And so that's where they ranged, but most of the scores were in the 20s, in the upper 20s. That's where most of the scores were. And so overall, I thought it was pretty good. I don't know all of your names, and so I'm still going to need a little bit of help as I pass these back. And what I would like for you to do, you can spend just a little time here today doing that, but what I always tell people when I pass back graded material is, one, you make sure I edit the points correctly. I'm a person, meaning I do things correctly, and sometimes I do things incorrectly. And if I made a mistake in adding points, that's what liquid paper is for. I make a change, okay? I verify that I made a mistake, but then I make a change, okay? And then if you have questions about the way something was graded, you can ask. You don't have to feel hesitant about it. And if I made a mistake in judgment, I look at it and say, oh, wait a minute, I'm wrong. Then I make a change. And if I didn't make a mistake in judgment, I say, no, that is what's written here. It's not right and needs some points taken off, and I'm happy with what I've taken off. Then I'm going to say, that's the right grade. I'm not going to be hesitant either way, but you can always ask. Okay? So those are the things I'd like for you to do. Or at least solutions to the problems that I have assigned, homework 1, are online now on Blackboard. So you can look what I presented as solutions. They're not the only way to do problems. Okay? But these are some of the ways that. Joanna, thank you. Tiffany is, I know Tiffany. Yep. No, you're not.
He's not here.
You're Steve. Jeremy Hank's not here. Evan. Now, if I had fallen there, and we got it on videotape, I would have made a lot of money. Ralph. We just can't fake. Thank you very much. No, I know. It often is untied. My eyesight's not too good with my glasses not on. Is that you, Andy? No? Andy's not here. Well, my eyesight isn't so bad. Richard. Okay. Stephen? Yeah. Aaron. Sarah. Thank you. Nathan, Matt. Somebody's named Nancy. Travis is here. There he is. Melissa's here.
I know it is. You do seriously.
Thank you. Al. Dennis. Yes, sir. You have a question?
Yeah.
Did I make it right?
I didn't put the B up here, I decided.
Do it. You'll head back to the nomination channel, okay?
Right now.
No, oh, well, I'll.
I see. I can hand it back to you after class, because I have the original.
Jennifer. And Andy was not here. Okay, so I'd like for you to take a little bit of a look at it. If you want to ask something, you let me know. If I miss at it already, Aaron's pointed out where I didn't grade something that he wrote down. I just said, well, where's this? Aaron said. He said, here it is. You just overlooked it. And I did overlook it, that's all. He had the right answer. While you do, I give you just a minute or two to do that. And then I want to give you a chance to ask questions about homework 2 that's due on the 23rd. And I don't know if many of you have had a chance to look at it. But for those of you who had, I want to give you a chance to ask questions. Sometimes it takes time to formulate a question. So if you're looking over it and saying, I don't know why there's something taken off there, give yourself a chance to ask about it. If you don't understand, then just let me know. I'm okay. Aaron, I will remember. You know, Aaron, I have my grade book. I can do it.
What's that word, you know?
It's out of 32 points. That one big problem. Does anybody want to ask anything about the homework? The old one. Okay. If you need more time to look over it, that's okay. That's
This is the one where I wanted, I should check.
Here's one thing that I would like to tell you about the exam on my handout. You know, I've given back this homework, and you see the scores on there. And I don't mean to say anything except things that are encouraging. That's what I'm going to tell you. The class is fast-paced. The material, in my opinion, is not very easy. Okay? That is my opinion about the class material. I'm teaching a probability graduate level class, and I think that material is easier than this. That's my opinion. So I'm not comparing this class to anybody else's class that somebody else is teaching. I'm comparing it to 2 classes I'm teaching. Okay? And so that's what I find. And the second term of this class is a little bit harder. Okay? I said I won't say things to you that are encouraging. That's my opinion, okay? Having said that, what I would like, with the realization that the course material is hard, fast-paced, and just to give you insight in terms of the experience that I had as a graduate student, When I took my first exam at LSU in topology, so this is a branch or subject matter in graduate level mathematics, the first exam was worth 60 points, okay? And I made a 30. That's what I made, 30. That's 50%. And so when I saw 50%, I didn't feel good. And the professor said, he didn't write down a letter. My assumption was I had failed. And I hadn't had any information about what was a letter grade in any of my graduate classes. And he looked at me and said, John, that deal big. He said, there were plenty of students who did better than you, but there were plenty of students who didn't. So that was what I was told. I'm trying to say something that's encouraging. Okay? So it's hard, and we people know that are doing the judging, in this case me. And so the grading scale is pretty wide. Is that okay? That's what I mean to stress here. Here are the scores from the first time that I taught this class for the test 1. So they're ranked in terms of the highest to lowest. Okay, so these were the scores. It's out of 100 points. So this is what I saw. That was the highest grade of them. There were 10 people. Those were the scores, okay? And that was me telling them, if you have these definitions, and that was 20 points of the test, you get it. And I probably told them one other thing was going to be on there for 10. That for sure it was going to be on there. And so there was 30 points that, you could automatically get. Does that make sense? So the material is hard. We know this, okay? The examples. So what I mean to emphasize is this. We got a wide range for which we can make good grades. Okay? The class goes quickly. Sometimes I think, well, wait a minute, maybe it'd be better if we just did 10 weeks over chapters 1 and 2. We'd understand that a lot better. But the people who are in charge of evaluating what a graduate level class would be, I'm not talking about a Shawnee State, would say that's not a graduate level class. You didn't cover enough material. Does that make sense? So the expectation in my mind of what's going to happen is you're going to get exposed to material that's going to be exposure. And you're going to say, well, I remember hearing about that. Okay? But I didn't catch it all. And that's kind of what's expected. And then some of you might catch more than others. Okay? But most of us aren't going to get them all. Yes, sir.
What were those letter grades?
I have. Okay. So I think I have. I might not have brought it. I have them written down, but I didn't bring them with me. Okay. So I think these three I think were A's, and I think there were some A minuses below that. Okay. But that's my grading scale. There's what I have. Now, usually what helps out is the homework. Okay, homework helps bolster the grades. Anyway, that's kind of for the setup for the class and what I wanted to say. Learn those definitions. I'll narrow down what you can expect. We'll go from there. Just do your job. Okay. Let me open up the floor to any questions people have about homework 2, if there are any. Yes, ma'am.
Could you guide me in assistance with number 8?
Problem 8 for homework 1 or 2?
Oh, 2. I thought we were on 2. I'm sorry.
We are on 2.
Okay. It's just a lot of words and symbols, and I'm having trouble getting through. There we go.
Okay. So here, just some kind of information about problem 8 was asked about, something to help. So problem 8 has to do with compactness. And so this is from homework 2. It says, consider, part A, it says consider the collection of open sets minus n to n, n running from 1 to infinity, n r, okay? With the usual metric. John, they can read, I'm writing all this on the board. Okay. Use, I should say, this collection of open sets to show R is not compact. And involved in that, we want to prove that R is equal to minus n to n. That's not right. The union of those. I better prove that. I did. No, I didn't. Well, there's a mistake. Okay. It's the union, it's n's element of natural numbers. So there's a typo. There's a handwritten mistake on the paper. Okay, so thank you very much, Christy, for asking about that. I'll send everybody an email with correction for that. Okay, so there's a mistake. Should be a U. Okay. Christy asked me the question, so I'm going to address my comments mainly to her, but I'll get other people involved, and please don't let me bother anybody by calling on you. If you say, well, I don't know, well, that's okay. We're not on the test. We're trying to learn something. So, Dawn, do you remember what it means to be compact?
No.
Okay.
I got that one.
Okay. Christy knows. Wait just a second. Does anybody else remember? What does it mean to be compact? Okay. That's all right. Christy, what does it mean?
I have that, and I'm just going to give you the definition, and then maybe help me through that. It says, if every open cover of K contains a finite subcover of K.
Okay. So that's the definition. So a set, K, is compact if every open cover of it contains a finite subcover. So anytime you give me an open cover of that set, it contains a finite subcover. What does it mean to be an open cover? Okay, that's the first thing. So a collection of open sets are said to be an open covering for K if K is the union of those open sets, and those sets are open. Okay? So I'm saying. In terms of a picture, if this is our metric space X, okay, that's our metric space X, and we're talking about something here called K. Okay, there's K. When we talk about open covering, we're talking about these, what I would draw as open balls. Okay, just in terms of pictures. We say, okay, look, we got this group of open sets. There, I drew these. And let's say we had infinitely many of them. Okay? And what has to happen for this open cover? So each one of these sets we're saying is open. What does it mean to be open? It means that every point that it has is an interior point. That means that every point in here, you can put an open neighborhood about it and be contained in the set. Okay? That's what it means. All right, so here, for K to be compact, if I had infinitely many of these little drawn things, that would be an open covering in that K would be contained in the union of all of these open sets. These open sets cover. You look at K, it's covered with them. If you said, can you see K if the open coverings had some kind of substance to them? No, because they'd be covered by those open sets. You wouldn't be able to see K underneath. Is that okay? So it covers, like a blanket. Okay? Yes, ma'am?
Can an open cover be contained inside K, or does it have to be on the border like that?
For it to be an open covering of K, you've got to be a collection of open sets, and K is contained in the union
of the open cover. So they might be exactly equal, K might be exactly equal to the union of them, but it might, the union of those open sets may be more, okay? But what I can't have is some spot of K that isn't covered, okay, by some part of some of those collections.
So I was asking, is can one of those dotted balls be inside of
Yes,
K
yes.
and not on the border?
Yes.
Okay. And I got you. I'm with you.
Can K be equal to the union since all of the
Not necessarily.
covers are open
Yes.
and K is closed?
Well, K, okay, so K is compact, and so compact of a metric space is closed. And so the answer is no, it can't be. That was a good question to ask. Because the union of open sets is
Open.
That's right. So that's a great observation. Okay? So, and when I say observation, it's not something we've said in class, but that is right. Okay, so that's what it means to be an open cover. For A, for this, A part, here's what we're looking at. We're looking at the real line, okay? The real line, I'm not going to draw it as a box. I'm going to draw it as a line. The real numbers, there it is. And what I've asked is to say, look at this collection of open covers. This collection of open sets. So it's centered about 0. Each set is centered about 0. And the first open set, if you will, first open set in there is from -1 to 1. Okay? So here, if someone were to label, you don't have to. I'm doing this because of questions that Christy came by and asked me about an index family of sets. Okay, one of the definitions. And so did Dawn. Okay? And so if I were to label I sub n as minus n to n, okay? If I were to label these I sub n's to be minus n to n, then n would be an index. And where the n's are coming from is called the indexing set. What do you think the n's are? Where do you think the n's are coming from? That's right. So here, n is an element. The book calls it j. I usually write down script n. That's what we mean by an indexing set. That's not such a big deal for this problem. All right, look, this is I sub 1. What's I sub 2? What's I sub 2? -2. What's the I sub 3? Come on, it's on the other side there. Okay, here's what I'm telling you. Each one of those sets, I sub n, is an open set. Okay? Every point of it's an interior point. And what I think is that if you union them all up, okay, you get a, so Aaron, my answer to you is not right. If you union them all up, you get R. So the union is equal to R. But you might say, boy, if the union is open, and you said compact sets of a metric space are closed. And this is open. It turns out that some sets are both open and closed. And the whole, this whole space is both open and closed. The whole metric space is. So my answer to you was wrong. Okay. So the answer is correct unless it's both open and closed. Okay. So I made a mistake in assuming that closed and open can't happen simultaneously, but they can.
If it goes negative infinity to infinity?
Here, the union of these sets is going to be R. That's what I'm going to say.
Yeah.
And I'm asking you to prove that. You know, of course, I had the typo in the problem. Let's talk about this for a second.
So R is closed.
R is closed.
Okay.
And R is also,
Open.
yeah, it's
Okay.
called a cloaking
Paradox.
set. It is. You could be neither closed or open. You could be both. You could be just one. Yes, sir.
So, were you saying that the union of those open sets could be greater than or equal to?
Okay. Yes. That's the right answer. But Aaron had asked me, could it ever be equal to? And I said, no, you're right. But then I'm wrong. Okay, what I said was wrong. They can be equal. Okay, here's an example. So I didn't think it through as well as I should have. So, you know, I said, that's a great observation. Well, it's wrong. It was wrong. Now, look, I'm asking you to prove this. And so, how do you prove two sets? These are sets. How do you prove two sets are the same?
They're subsets of each other.
They're subsets of each other. Everything in here is in the right-hand set. Everything in the right-hand set is in the left-hand set. Okay. So here, let's think about this. First, so claim R equals to the union for minus n to n. That's a claim. Something. That means that this collection will be an open cover. Okay? They're open. I'm telling you they're open. And if the union is equal to R, it's open cover. Okay? And then what our whole goal is to show that R is not compact. And the reason it's not going to be compact is because for this particular open covering, you can't find a finite subcover. There are open coverings of R, okay, for which there is a finite subcover. But to be compact, it's every open covering has a finite subcover. Every one of them. And here's one that won't. Okay? Is that okay with everybody? Okay, that's the definition. Those are some important words that are being said. I can find an open cover R that has a finite subcover. That doesn't make it compact. That does not make R compact. What makes R compact is if every open covering has a finite subcovering. So it would not be compact if I can find an open covering that does not have a finite subcovering. And I'm telling you that's an open covering that doesn't have a finite subcovering. Okay. All right, first of all, this is the first claim. We're going to go slow today. This is the first claim. Well, how do I prove it? Well, I let X be an element of R. What have I got to do? I got to show that X is in this union. What does it mean for X to be in this union? It's got to be in one of them. Is that okay? Okay. Well, here's what I'll say. I'm going to look back. One of the things that I would say is the set of natural numbers are not bounded above. And so there's going to be an n bigger than absolute value of X. I'm just going to write that down. Since J is not bounded above. Then there exists an n sub naught element of J such that the absolute value of X is less than n sub naught. So that means that if the absolute value of X is less than n sub naught, where does X got to be?
So that one more time.
Here's the absolute value of X is less than n sub naught. Solve for X. Listen, we teach algebra, ladies and gentlemen.
And negative instances, which means zero.
Is that okay? What's these sets? They're the collection of all intervals that go from minus n to n. So this one of these intervals. So X is in Is that okay with everybody?
Should be negative n sub naught on the left.
Oh, yeah. Boy, that's terrible. Thank you very much. So X is in one of these open sets. Is that okay? The other way, this showed that R was a subset of here. Okay. Now, if we let X sub 1 be an element of this union, then what does it mean to be in this union? Ashley, what does it mean to be in the union? Do you remember?
You have to be in one or the other.
That's right.
Okay.
You have to be in at least one.
Yes.
So that's beautiful. So here's what I'll say. So there exists an n sub 1 element of J. There's some guy in this indexing set such that x sub 1 is an element of minus n sub 1 up to n sub 1. Now what are these? These are the collection of all real numbers between. So listen to my words. This is a collection of all real numbers in between here. So if x is in here, x has got to be a
Real number.
Listen, I did 2 sessions of the probability class that I'm teaching already, face to face. And I did something that I didn't like. I said something that was incorrect. I said something today that was incorrect, but I didn't feel so bad about this. I said something to them that was incorrect, but really a PAL 3 type of topic. I just got confused about it. Okay? We're talking about graduate level. I got confused about it. One thing I was mad at myself about, not only saying something wrong, was I was sure that I was not positive. Okay? I didn't have a good handle on it. I think we all can relate to this. I was like, wait a minute. But I wanted to move on. I said, well, I think it's just this. Okay? And then later I went back and looked at it. I said, oh my God, it's wrong. It's terrible. I'm going to hell. And so what I was mad about is that I didn't do what I believe is something fundamental that helps me. And that's take my time and say, wait a minute. I've written, I don't do that here. I've written down, since J is not bounded above. That isn't something that I've told you, but it's true. J doesn't have an upper bound. So you think of natural numbers, there's no number. But I'm going to go back. So I want all of you, mathematics is a beautiful thing. That's opinion. In that logically you can jump all over it, stomp on it, and it's going to be able to withstand whatever you say. Because people have gone through it and said, this is logically sound. Does that make sense? So somehow I got to get some reason really why I can do this. And so what I'm thinking of is that we had something called, I'm looking in our text, it's called the Archimedean property for R. I'm going to write that on the board, and just that comes into my mind that it might be what I need to say here, instead of saying J is not bounded above. I'm okay with that statement. But I want to look at this Archimedean property for a second. Here's what's it. Okay, it says, so one thing, let me write this here to the side. Get a little more space here. I'm just going to write down the statement. Let's see if it applies. If X is an element of R and Y is an element of R and X is greater than 0, then there exists a positive integer n such that nx is greater than 1. Now I want to tell you, I've written it on the board, and it applies. Okay? How does it apply to this statement over here? Well, the absolute value of x is going to be my y. Okay? So y is a real number. Absolute value of x is a real number. Is that okay with everybody? It says if you give me some positive number, then there's some integer that I can multiply that positive number by and get bigger than the absolute value of x in our case. I give you a real number that's positive. 1. I give you 1. X is 1. Y is the absolute value of? X. Okay. So that means there exists an integer, a positive integer. That means it's a natural number. So I can multiply 1 by and get bigger than absolute value of x. So it's this fact that gives it to me. Is that okay? I didn't make that fact up. It's something we went over. Is that okay? So that's the reason I can write down, hey, J is not bounded above. You know, I can get this in. Okay? This n sub naught. Is that okay? Now, I really like what I just did. I didn't say, oh, here's something that you should, it's in the book. Here's what I can point to. This is the reason that I have the ability to write down what I did. Watch. Is that okay? And that's what we should be doing.
Yes.
Is that okay with everybody? Okay? That's what we should be doing. So when I'm up here and making videos and I write down lines and you say, what the heck is he talking about? Which would be a normal thing. Okay? Because it's coming fast. I'm not putting every detail in the world down. Okay? You say, why can he go from that line to that line? You ask yourself. And if you don't know, you dig a little bit. Look. And if you can't find it, you ask me. And my job's to tell you. Okay, does that make sense? Okay, all right. So anyway, there we go. So here we've shown that these two guys are equal to each other. So this collection, is an open cover for R. That's what we've shown. Now, what we need to show next, Christy, is that it doesn't have a finite subcover. And so the way that I would do that was suppose that it did. And then I want you to look at them. So what are we saying? What does it mean to be a finite subcover? That you only need finitely many of these guys to cover, in this case, what are we trying to cover? The reals, that's right. So we only need finitely many of them. But if you have finitely many of them, you can kind of index them by I sub n. If you only have finitely many of them, think about it. I sub 1 is contained in, which is contained in, when you union just finitely many of them, if you union them, let's say I take the first 5 of them, and I union them up, what do I get?
It's just I sub 5.
That's right, I sub 5. So here, if I didn't just say I took 1 through 5, I took 1, 37, 23, 42, and 11. And I union them up. What would I get? The biggest one. That's right. That's the thing we would concentrate on. Is that okay? So what I want to tell you is if you take finite, you say, I take finite. I take I sub 1, we write down I sub n sub 1, I sub n sub 2, all the way up to I sub n sub j. It's finite. So we end someplace. J of them. So I got it. Then when you union them up, they're going to be contained in I sub the maximum of 1 through, that's exactly right. And that means it's going to be contained from minus j to j. Do you get the whole real numbers when you union those up? No. Because there's a lot of numbers bigger than
J.
Christy, is it okay what I just said?
Mm-hmm.
Now I want
Good
to...
process, but
Okay.
yes.
Okay, that's the proof. Okay, I showed that it's not compact for part A. That's it. Okay, what does it mean to show that it's not compact? Is that you find an open covering that does not have a finite subcover. To be compact means every open cover has a finite subcover. So Sarah, if I look at this, if I look at R, so if I look at R and I say, hey, R is equal to, if I look at, I'm looking at R. I look at this finite, I look at this cover. I look at the minus n to n. Those guys, that's part of it. Union, the set that contains, let's say, minus infinity to 3, that union with one other set that contains, let's say, 4 to infinity. Does this have a finite subcovering? Okay, all of this will cover, if you union all this up, you get R. Because if you just union this part up, you get R. Okay, so if you throw in these extra sets, they definitely going to make sure that you got R. Open sets over things that are already covered. Does it have a finite subcover? Yes. I take, from, I meant minus 3. Not that it makes a difference. But all of this is covered by one set. All of this is covered by one set. So I just need to cover this. Does that make sense? By these guys. And I only need, I could pick one that would do it. Which one? Well, that didn't fit one of these guys, actually. Remember, they end and start with the same. Negative 5 to 5. Is that okay?
Okay.
So if I look at minus 3, if I look at minus 5 to 5, and I say, hey, if we take those 3 sets, doesn't it cover all? So that particular open covering did have a finite subcovering, but ours not compact, because there exists an open covering of it that does not have a finite subcover. To be compact, every one of the open coverings have to have a finite subcover. Not just one of them. Every one of them does. Is that okay? Melissa, did you want to say anything? or ask anything, or I don't get anybody to do this. Anybody can talk.
No, I think I got it.
Anybody can have a chance to think, okay? I'm not supposed to. We're asking you to think, process a lot. You gotta be given a chance to think. Okay? I don't have to be in the business of saying.
Would you be able to give an example of one that doesn't have a finite subcover?
Yes, we did. That minus n to n doesn't have a finite subcover. That one we, don't let me bother you, Sarah, but the one we started with, okay? The one that was from minus n to n, didn't have, because you said there were only finite many of them?
Right.
No, it would only go up to the biggest n that you picked, and the small.
Okay.
Is that okay?
Yeah, I get it now.
That's the
Is that okay with everybody? Christy, I did the problem. I don't know if everybody understands, but I did the problem, okay? I answered part A. Okay, there was more to this part, Christy. Do you want to see more, or me to say something more? I'm not going to do the rest of it. I might get in.
I'll let you know. I'm not even sure what to ask,
Okay,
because I'm still processing that.
okay. I hope that's okay what I said. Was there anything else that somebody'd like to see from the homework? Homework.
Dr. Whitaker,
Yes, ma'am.
what lectures does this homework completely cover? Does it go from 10 or 11 to all the way to 17?
He doesn't quite make it to 17.
Okay, okay.
I think it actually goes through 13 or 14. It might go through 15.
It doesn't. I don't think it includes anything from 16. Okay.
Okay.
I don't think it does. It might, but it definitely isn't gonna have. It's not gonna have anything from 17.
Okay.
I just have another question about this, please. If we're writing this up ourselves, as we go back through it and write it up for ourselves, are we allowed to use pictures like that in our proof to explain
No.
things, or?
No, ma'am. In terms of the Christy.
Because the pictures help me understand it, but
Right.
I can't get the words out.
Well, here's what I'm going to tell you. It may allow us to say, okay, so you said something I like very much. So, Christy, part of the proof-based class is developing the skills for which we write down proof. Okay? And so, I'd like to look at a particular problem a little later today and show you the picture. And I didn't write down any picture associated to it when I did the proof. So something we've already done. And what we want to do is we want to be able to write down symbolically what's occurring, describe it. Even if we have a picture that, for us, describes it, we want to write down symbols. Okay? So that's what we want to be
Yeah, I
able to
think
do.
that's where my biggest problem is, that I can kind of conceptually understand maybe what some of this is, but then you can't write it with the such that's and there exists and elements of.
Well, one thing that I can tell you, as in doing anything, experience helps. So going through it, working, asking, looking at how somebody else does it. Listen, I'm going to tell you a philosophy. I'm telling you an opinion, not a mathematical fact here. Okay, when somebody asks me to do something, and I have no idea how to do it, and if I want to be successful at something, what I do is I find somebody who was successful at it, and then I just do what they did, if I can. Because if it worked for them, they're not special. It'll work for me doing the same thing. Does that make sense? Now, I might not be able to do what they did. I can't play basketball like Michael Jordan. I can't make the shots that he could make. Okay? But I can try to emulate what he did. Does that make sense? Okay? So, in this setting, I'm one of the people, being the teacher, to try to do what that proof is. And what I'm doing is emulating that writer, the author. Okay? Because he's written the book. But I'm adding more details so that I can help him. It helps me understand. Would anybody else like to ask a question? I've got things that I can show you that I want to show you, that I hope is helpful. But I want to ask, these sessions are supposed to be so that you can ask anything that you want. And then when we run out of time, I'm going to help guide you. Okay? So does anybody want to ask me something else? You're welcome to. I'm hopeful that you do. Okay, let me ask this question. How many of you, you don't have anything to worry about. Has anybody, how many of you haven't started your homework yet? Okay, that seems kind of normal to me. You got other classes and you hadn't started the homework. Does that make sense? I buy it completely. Need to get started at some point, okay? Okay, let me look at the first problem for you. Okay? The first problem. On the homework. Let me look. Okay, so let f be a function that maps x into y. Okay, so we symbolize that with f goes from x into y. Let g, doesn't say it's open cover, g sub alpha, looks like this. Alpha is an element of an indexing set A. Be an index family of subsets. Of y. Show f, the inverse image of the union of the g sub alphas, equals to the union of the inverse images of the g sub alpha. That's what it says. Well, the first thing that I would do, okay, look, I'm the teacher. And so what I would hope for, people doing exactly what they need to be doing, you'd be following the lectures, and you'd be writing down the definitions, learning the definitions, and we'd go the next section, and you'd understand it immediately because you knew the definitions and knew the material right before it, and it all makes sense. That never happens. Okay? That never happens. Your teachers, your students don't do it. It just doesn't happen. Okay? It's hard material. It just doesn't happen. So usually what happens is this. You have this homework problem and you say, I don't know what these things mean. Let me start looking. Where are these symbols appearing in the notes so I know what it means? Okay, so involved in this problem might be an index family set. I'm telling you, that isn't such a big deal. We've seen some of it here previously. But the first thing I'd like to say is if you have f going from maybe A to B, then if, let's say, E is a subset of B, then the inverse image of E under F is defined to be all the little a's in big A. So this is a definition that we need to know to be able to do the problem. Such that f of A is an element of E. See, I want to talk to you about what does this mean. So I'm going to say, I'm talking to you, I'm talking to everybody. Okay, so what do we got? We got F. What is it? It grabs some points of A and sends them into points of B. That's what it does. It's a function. Okay, Michelle, that's what it does. And it says, hey, look, if you take something over here in B, and you say, what is F inverse image of that set over here in B? What it is, it's all the input values that F grabbed that send them to output values that were in B. Okay, that's what it says. And then what if let's say L is a subset of A, then what's F of L? F of L is equal to the collections of all B's element of big B, such that there exists an A element of big A with F of A equaling to B. So what's F of L? It's the output values that came where the input values were from L. That ain't going to be involved in this problem, but it's something associated in the same area. Okay. Okay, so we're going to try to do this problem. Okay, so I want to show these two sets are equal. How do we show two sets are equal? So it's Richard, right?
Right.
Okay. Richard, how do we show two sets are equal?
They're each a subset of the other.
Beautiful. That's correct. That's what we got to do. We got to show the left-hand set, Tiffany's a subset of the right-hand set, and the right-hand set's a subset. How do we do that? We show that you give me any arbitrary point in the left, it's in the right. You give me anything arbitrary in the right, it's in the left. So it's two things. That's what I got to do. Okay. So here, I'm going to start. I'm going to say, we want to show these two things are equal. Well, let me give some kind of good name, symbolic name. Let. All right, what does this set live in? What's it a subset of? Okay, where are the G sub alphas? G sub alphas are in where? Of what? The G sub alphas are in what? So when you union them up, you're in what? Those are output values. If you take the inverse image of them, you get X values, input values. Okay? So these guys are in X. Is that okay? Alright. Okay. So I'm going to let X of 1 be an element of the inverse image, that's what we call it, of the union of alpha element of A, G sub alpha. Alright, here's what I'm going to do. It looks complicated. Okay? But it's this. It's this definition. Okay, what does it mean to be in here? You're in the domain space. You're in the input values. And what quality do you have? Is it everything in here? No. It's just the guys that are in the input. It's just the input values such that their output values are in the E. E is what's in parentheses. So the output value of X sub 1 is going to be in?
Say that again.
The question I'm asking is the output value for X sub 1. The output value for X sub 1 is going to be in what?
G sub.
Not G sub alpha.
Why?
Well, it is going to be in Y, but that's not restrictive.
Union of G sub.
That's what it is. It's the guys in parentheses right here. So maybe you meant something different than what I heard said, but I heard people say G sub alpha. That ain't quite right. It's the union. And it was the output value. What's the output value of X sub 1? That's right. Is that okay? I got to move the camera. That's right. Thank you very much. Thank you, Michelle. So we had this problem. There it is for those of you not here. Good enough. And we moved on. Thank you. Okay. What does it mean for this guy to be in a union? What's it mean to be in a union?
At least
You're in at least one of them. So there exists an alpha sub 1. Hey, matching with this X sub 1. So that's why I'm thinking, Christy, in terms of developing my ability to write proofs. I'm going to have something now that's match. Okay, there exists an alpha sub 1 element of A such that F of X sub 1 is where? What about it, Aaron? Where should it be? G sub alpha sub 1. Joanna, that's right. I mean, that's your name. Angie. Okay. Angie, thank you very much. That's right. Okay. Okay. All right. Now remember, we want to talk about X sub 1. We want X sub 1 to be in this guy. Does that make sense? So I want to get back to x sub 1 somehow. I moved to f of x sub 1. But f of x sub 1 allowed me to get to the g sub alphas. Is that okay? Now I want to talk about x sub 1. Well, look, if f of x sub 1 is in g sub alpha 1, what can you tell me about x sub 1? That's exactly right, Aaron. That's exactly right, Tom. So that means that x sub 1 is an element of the image, of the pre-image of g sub alpha sub 1. That's what I should say. Is that okay? Why? Because it's an input value that f would grab and send it to something in g sub alpha sub 1. Yes, sir. That's right, Steve. Is that okay with everybody? Remember where we're trying to get it. We're trying to get it into a union of inverse images of these g sub alphas. But it's in one of them. So if it's in one of them, it's in the... I just say thus. X sub 1 is an element of the union of over all alphas. Alpha sub 1 is one of these alphas. Okay?
We need to say that that's inverse of the union is a subset.
Yes, that's a good conclusionary thing. Aaron, I told this to Christy the other day, yesterday I guess it was. What you said is what I should write. But what came to mind when you made that comment was, you know, when you're learning how to drive, your teacher would tell you, oh, you need to put your hands on the steering wheel, 10 and 2. And then once you get used to driving, you're not thinking that way. And so, for me, I'm done with that part. But you're right. The right thing to make sure we understand is this is telling us. That's exactly right, Aaron. So, this says that the pre-image of the unions is a subset of the union of the pre-images. And then we have to do the other way, which I'm not going to do.
On the next to the last line, is that G sub alpha not with the 1 anymore?
No, it shouldn't be with the 1. I made a mistake. That's right, my symbol was incorrect. Is that okay with everybody? And I'm not doing another side. But that's what it means. Is that okay with everybody?
What was you talking about?
Yeah, what was this?
Well, I made a typo. I had a 1 here, and it shouldn't be. This is for the alpha's moved. It isn't just for alpha sub 1.
Right, okay.
Is that okay with everybody? Is that okay? Okay. Listen, I want to emphasize and encourage you. It's not an easy class. You ask, why is this statement true? Why is this statement true? Okay. Some proofs, they're innovative. Some proofs are kind of follow your nose, follow the definitions. And I want to concentrate on a few of those. Okay? I want to concentrate on a few of those. I've got something written down. We've done in video lectures. I just want to go over with them with you to try to emphasize what I would consider a good way to study for class, a good way to try to learn it. So if it's okay, I'm going to move on to those things. Okay, the first thing I want to show is one of the things that we said. We had a theorem that we did in video lecture that had to do with having some collections of open sets or closed sets. And if you had an arbitrary union of open sets, that made it open. If you had an arbitrary intersection of closed sets, those were closed. If you had a finite intersection of open, okay, fine, that was going to be open, finite intersection. But you might, and then if you had a finite union of closed, that was going to be closed, okay? Okay, I'm going to look at one of those. First. So, let us revisit this statement and proof. And the reason I'm doing it is trying, like I said, to give you insight of what I would try to study. So here's the statement. Here's part of it here. I just write down one thing. If G sub alphas are or is a collection of open sets, then the union is open. Okay. So I had kind of begun, preface this proof or this statement by saying we were going to look at things that were straightforward, not innovative proofs, arguments that just kind of stem from the definition. We've got to know the definition. Well, here I want to show that this union is open. What does it mean for a set to be open? What's its definition?
All of its points are interior points.
That's what it means. So every point that's in this union is an interior point of that set. What does it mean to be an interior point? Neighborhood about it that is contained in the set. That's right, Angie. That's right. Okay. Knowing that information tells you what you need to do, or if you can do this, you've shown the logical argument. Sometimes we can say, if I can do this, I have it. We can't do it. I mean, we can't. It's not an easy argument to make, and we have to go about it through a different means. Does that make sense? Just because you find someone, oh, this will be good enough to show, doesn't mean you can show it. Does that make sense? So we have maybe other ways of looking at the problem. Okay. So here, I'm going to back up just a little bit. I'm going to say, well, you told me what it meant to be in material. So I'm ready to prove it. I'm going to say, well, look, I know what I got to do. Every point in here has got to be an interior point. So that means every point that I got here, I've got to be able to get some neighborhood about it that's contained in that set. Okay? Contains that point in that set. Okay, well, how am I going to show it for every point? I can't. So what we do is we say, well, just give me some arbitrary point. Nothing special about it. Doesn't have any characteristic except it's just in the set. So if I can do it for any arbitrary point, it means I'm doing it for all the points. Does that make sense? So let X be an element of these unions, of this union.
Dr. Whitaker,
Yes, sir.
can we say at the beginning of that, let X be arbitrary?
Yes, you can.
Also as, and then give that.
Let X be an arbitrary point in this union.
Because at the very end of the proof, we always said, since X is arbitrary, I mean, in other words, it's the same.
Yes, that's right. And eventually,
I forget about it at the end.
well, eventually, we don't care because we know we get kind of, as the analogy of driving, you get so comfortable, you know that you're just saying, you give me some arbitrary point. That means we're doing it for any point. We're doing it for all the points. Okay? It's okay, Aaron? Okay. But yeah, you can say that X be an arbitrary point in this union. Okay. We want to show it. You can write that down if you want to, but I'm not. We want to show it's an interior point. Okay? Well, first of all, here's what I'm going to do. I'm going to say, if it's in the union, then it's got to be in
At least one of
one
them.
of them. Thus, there exists, this is the way I've expressed this, Christy, there exists an alpha sub 1 element of A such that X is an element of G sub alpha sub 1. That's what I'd say. It's got to be in one of them. I'm calling the one that it's in, that I know it's in. It might be in more, but the one I know it's in, I'm going to call G sub alpha sub 1. What do I know about G sub alpha sub 1?
It's open.
It's open. Yeah. It's open. Since G sub alpha sub 1 is open, and X is in it, I'll write that down. I haven't been writing down this much detail. And X is an element of G sub alpha sub 1. So what can you tell me about X?
It's an interior.
It's an interior. And you're getting to another conclusion. It's correct. Okay? then X is an interior point. Of G sub alpha sub 1. Well, what does it mean, Aaron, to be an interior point?
There's a neighborhood about it.
So there exists a neighborhood of X. Say, I'm going to give it a name, n sub r of X, that's contained in,
G sub alpha sub 1.
you're right, but we get specific because there's a bunch of sets running around here. That's right. So one of the things, and let's see, you were Angie, you must be Al.
Yeah.
Okay. One of the things that Ali said, that I would comment, is that even if you know what you mean, using a pronoun is not beautiful in mathematics. Now I do it, we all do. It, that. We have to say what we're talking about because there's a lot of things running around. I do it too, but it's that tough in math because there's lots of things running around, but we have to get very specific. Okay, so R sub X is contained in G sub alpha. What am I trying to do? I'm trying to show that X is an interior point of this guy. That means I've got to get a neighborhood of X that's contained in here. Well, wait a minute, I think I just did. Because if that neighborhood, if every point of that neighborhood I just wrote down is in G sub alpha, then every point of this neighborhood is going to be in the unions. Okay. That's what I write. So n sub R of X is contained in the union of the G sub alphas. And so what does that tell me? So X is an interior point of this union. And what does that tell me? X was just an arbitrary point belonging to that set. So what does that tell me about that set? Yeah, that set is the union of the G sub alphas. So the union of G sub alphas is open. Now this is something we did, but I want to tell you, for me, this is one of the easy statements, okay? It's one of the easy statements. Yes, ma'am.
We tell our students the same thing, not to memorize, but looking now at the experience of having enough proofs, if we're going to talk about a union, we kind of want to talk about a single set, and then if it's in that single set, it's in a union, and if we're talking about equivalent sets, we want to show that they're subsets of each other. Is that kind of the direction that you would go if you were to come across proofs that have this kind of language?
For the union, yes. The equivalent sets means that there's a one-to-one correspondence between them.
Okay, well, that's not the word I meant to use then. I meant to use whatever we just did a minute ago, we said they were equal to each other.
Okay.
But
Yes,
the inverse
they're
sets.
subsets of each other.
So if we're
Yeah.
talking about equal sets, we kind of want to work on subsets. If we're talking about unions, we kind of want to individualize and then say if it's in one, it's in all, or if it's in the union, then it's got to be in one of them.
Yes.
That's kind of the direction we want to.
Exactly, yes.
When we
Yes,
see
ma'am.
those words, that's kind of what we want to start.
Yes,
to
ma'am.
do.
So, so if you want something to say that is something, a fact, when you say you're in the union, you're in at least one. Right. And that's what we should be thinking, okay? That's the way we proceed, okay? And I'm going to say this, and I don't care that I'm on tape. There's nothing wrong with memorizing.
I know, but I can't memorize this, because then if you change all the letters and numbers and stuff, I have trouble transitioning it. But if I can get to the concept of union means it's in one, it's in all, or if it's in all, it's got to be in one.
Right.
That's a concept that I can put into this language.
Yes, ma'am, that makes sense. And so what allows us to get that idea is knowing the definition of the union, what it means to be a union. So I would say this, memorizing that definition lends itself to saying this is the idea.
But that's, I mean, but like I said, this is one of the easier ones. When you start getting into compact and it's got open covers and subcovers and finites, that's got multiple layers of
Sometimes,
memorized.
and I'm gonna do one today, in just a little while. But yes, ma'am, that's right. And it's impossible for us to memorize the course in this period of time. So we're not looking to memorize. We are looking to get ideas. That's what but for the definitions, I'd say we're not, to be able, here's what I'd like to say. To be able to make logical conclusions, you have to start from some truths. And so if we don't memorize what truths we're starting from, we can't logically proceed at all. So there's some basis from which we start. And you say, you got to know what the starting place is. Does that make sense what I said? And so those are things I said, we got to memorize that. Does that make sense? Because we're not going to logically, somebody said artificially, these are things we say are true. They didn't have to. Okay? And from there we go. Is that okay? And I don't mean to get in some philosophical debate, how to teach. That's not, I'm just trying to tell you things that I think would be helpful. That's my job. I would like to do another. These are things we did, but I just want to, how do we proceed? So I've got that sheet of paper. Do I have it laying around somewhere? I put it over there. Guys, yes. Okay. I'd like to do an if and only if statement that's been done in videos. Well, what happened for me, I thank you very much for offering. But I want to tell you, Michelle, the week before we started, so I'm going to take 2 minutes of time. The week and a half before we started, I used the remote, and the video would cut off. I don't know if you know the first 2 videos maybe of this class, is that right? I said, it cut off. Well, what was happening was this. So I'm going to take 2 minutes to tell you the story. What was happening was I was talking because I didn't know it cut off. And so I went, the full whatever. Okay? And I was using the remote, and apparently if you press one button too many times in a row, it cuts it off. What a stupid aspect to have to the machine, to the remote. So I kept going, and I didn't know. And then I didn't know that's what was happening. So I said, what am I doing wrong? So I did, video 1 that you saw was a well-prepared video because I'd done it 6 times. You think I'm kidding, but I'm not. And I would do it for an hour, and then I'd find out sometimes only 10 minutes were taped. So, I wasn't feeling good. So I wasn't very nice to the people who were in instructional technologies. I wasn't mean to these people, but I was more like, I'm starting to get a little aggravated here. I'm not going to be able to finish the class. This is going to be awful. So, I'm taking 6 hours to get 15 minutes done. This is beautiful. So I just didn't have it today. So I'm ready to throw that thing away. We're not going to use that. And it took me. I'm going to say this other aspect to it. It took me 6 hours to say, you idiot. I'm talking to myself. You turned the camera. What are you using the remote for? It took me 6 hours of messing up to say, watch. That happened, okay? And so then I didn't tell very many people because I was so embarrassed that it took me that long. Now I'm telling you the truth. That's what happened. I'm glad we're having some enjoyment. You is open if and only if. You complement is closed. Okay. This is if and only if statement, so it's got 2 parts. Okay. So thank you for your offer, Michelle. We're not doing it. So here's what we got really 2 statements to make in an if and only if statement. And I can't remember the first video very well, but we went over proving techniques, and one of the statements that we could be asked to prove is an if and only if statement, which means you really have 2 if-then statements. You got if the first part, then the second, and if the second, then the first. Here, we're going to this is this direction. what does that mean? We assume the first thing. Let U be open. We want to show U complement is closed. Okay, look, I forgot the proof. I did it just to make sure I could do it right before class, or an hour and a half before class, but I forgot. So I'm going to try something. If it doesn't work, then eventually I'm going to look it up if I don't get it, because we're not going to waste all the time, okay? But what I would say, everybody in the room, that's natural to do, is to say, well, what does it mean to be closed? What it means to be closed is that you contain all your limit points. So what's a limit point? A limit point is a point for a set is a point such that every neighborhood about it intersects that set at some point besides the point of interest. Okay?
Every neighborhood about it, what?
Let me write it down so that I'm not so general. I'll write down something specific. Just a second. Aaron?
That was, limit point was one of the things in the videos that kind of confused me, and I was going to ask you, could you draw a pictorial version to make it click? Because that was one of the things that I had trouble grasping, but your pictures usually makes it make sense for me.
Okay. Well, it's tough to draw a picture for everything.
Yeah.
But here's kind of what we have in mind. So first of all, let me write down the definition. Hold just a second. I can get your name. What's it start with?
V.
V. I know what your name is. It's Dennis.
There you go.
I got it. That was me turning around like I know it. Okay, so definition. So here's the definition. Let X be a metric space E be a subset of X and P be an element of X. Doesn't have to be an E here.
Yeah.
Okay? Then P, so let's put period. P starts the sentence. P is a limit point of E if, okay, so it's if every neighborhood of P intersects E at some point Q different from P.
So if E is open, then it has to be, the limit points would have to be contained inside, or whatever the P is would have to be inside, correct?
No. So here, I guess what I'd like to tell you is this. So here, let's look at 0 to 1, open, okay? Doesn't include endpoints, okay? So to be open means every point in the set is an interior. Well, I want to tell you 1 is a limit point. This is set E. 1 is a limit point.
Yeah, that makes sense.
Of E. So, Aaron, one way of thinking about it, it's not the only limit point of E. So it's 1/2.
It's a 0. But 1.0001 would not be.
That's right.
Gotcha.
Okay. So wait a minute. Aaron, it's tough to draw a picture here, but things on the border we're thinking of as limit points, okay? But here, the 1.001, that's what Aaron said. So if I think of this from 0 to 1, and it's 1.001, we're real close, okay? Real close. But if you get a magnifying glass out, it's like over here. There's a gap. And if there's a gap about it, then I can find a neighborhood about 1.001. I can find a neighborhood about it, equally spaced region about that point that doesn't intersect
0 to 1.
That's right, E, 0 to 1, that's right. Is that okay? And so that's why it's not a limit point. Is that okay?
So the set can be open or closed. You can have parentheses or brackets, and that's irrelevant for a limit point.
So here, the limit points of E 0 to 1 open, are they the same as the limit points from 0 to 1 closed? The answer is yes.
Okay.
In this particular class.
Okay. That's what I was asking for. That's what I was curious about.
So then, would every interior point also be a limit point? Right.
Okay, so here, that's the question. So, okay. And so I have to think about this for a second. Maybe I should be able to answer quicker. But is every interior point also a limit point?
The answer would be yes, because an interior means it has a neighborhood that is within that set.
I think in the general topology type setting, the answer may be no. There can be some strange things formed, okay? So I don't want to answer very quickly, okay? So I want to think about that. In this case, all the interior points are also limit points. Okay? I don't want to give I don't have an answer. That's what I'm saying. I think there are settings for which we get strangeness.
Because I would have never thought of 1/2 as being a limit point. I would have thought of 0 and 1 being your limit points and not even think of an interior point as a limit point.
It is in this case. It is.
Which is going to clear up some things for me in your proofs. Okay.
Every neighborhood I draw about 1/2 intersects E at some point besides 1/2. Okay. Anyway, we do the proof. So I'm thinking, okay, let P be a limit point of U closure, okay?
Is that U complement?
U complement, not closure. I said wrong. U closure. U complement. We want to show so we want to show P is in U complement. What I want to stop and say something to you that makes me hesitant, okay? Say something to you, Don, to the question Don asked, was the following. You know, Don would think, oh, every interior point must be a limit point, okay? What I'm thinking is there might be setups, metric spaces, I'm not sure, where the neighborhood of a point is just the point itself.
Well, that's what I was just thinking. If your set is made up of individual points,
Right.
instead of an interval of points.
Yeah, but it's not that. I'm talking about the metric space. Might have R's might have radius such that when you talk about the neighborhood of that R, about that all it consists of is just that point. Okay, I know you're thinking individual point. I know.
Okay.
But that's what I'm talking about. That the open set only consists of one point itself. Okay.
Yeah, that's the example I looked about.
Yeah. And so if that's the case, then the interior point would not be a limit point.
Yeah, so they call it a discrete metric.
Yeah. Yeah. So there's things like that can happen. Okay. So it's hard to make generalizations. Okay. It's hard. Good. And so, but it's good to think about it. But it's you gotta be careful. Okay. All right. Look. So we want to show what? We want to show P. So it's a limit point. We want to show. We want to show P is in U complement. Is that okay? Okay, that's what we want to do. Okay, so what does it mean to be, I don't know if this is going to work, but what does it mean to be a limit point? So, since, I'm just following my nose and hope something falls out. Okay? Since P is, well, that sounds terrible, didn't it? Since P is, I can't wait to see this on tape, is a limit point. Is a limit point of U closure. Then every neighborhood of P contains a point Q not equal to P with Q an element of U closure. That's what we got. Okay, these are true things. I don't think it's helping us. Okay? I don't think so. So wait just a second. I won't give myself time. Think about it. Okay, so Q is open. I hadn't used it. Used open, right? Okay. Okay, what does that mean? So every neighborhood of P contains a Q with Q in U common. I said, I don't think it's helping us, but wait a minute, maybe it is. What that tells me about that neighborhood, I'll tell you one thing about that neighborhood. It's not in U. Is that okay? Because it contains something that's not in U. Is that okay? So every neighborhood of P, I'll say it this way. So for each neighborhood of P is not a subset of U. So there isn't a neighborhood of P that's totally contained in U. Is that okay with everybody? There doesn't exist a neighborhood of P that's in U. So you know what that tells me? P is not an interior point of U. Not done. Well, wait a minute. If it's not an interior point of view, remember U is open. So what does U have? The only thing U's got in it are interior points. So what does that tell me about U? What does that tell me about P? Okay, so think right here. P is not an interior point of view. The only thing in U are its interior points. If it's not in U, it's in. And that's what we were trying to show. Is that okay with everybody? That's one direction. Is that okay? I was a little worried, Christy. I think, oh gosh, this doesn't seem to be helpful. Okay? But it did fall out. Is that okay with everybody? Okay. I'm going to say something's an opinion again. And you say, I don't believe that. Okay? But I'm going to say an opinion. We were talking about, learning the material. Okay? And memorizing or going over. Sometimes I hear teachers say, I'd like for my students to be able to figure this out. I'm not going to figure out the same thing Einstein was able to do. Did you guys hear? It's just not going to happen. But that doesn't mean I can't study his work. But it's not going to be a discovery because I'm not going to have his ability. Does that make sense? It's already been done. So there's some things out there that I can do that other people did. Okay? That I can be put in a situation and I can discover, and that's a good learning experience for me. But some of it's going to be too complicated. Does that make sense? And they've already done it. So reading it and understanding it's going to be enough if we get that. Does that make sense? I think a lot of this course falls into that category, and that is that difficult. Is that all right? So that's what we're looking to do. Can we just understand what somebody else did? Can we reproduce it? Not that we could have come up with it ourselves. And then we get good enough at mimicking, reproducing, thinking like that. Maybe we come up with some things that we didn't think of. That's what I think the idea is. All right. So we've done half of the proof. That's great. We still got time. What's the other half? So here, let you complement be closed. Show you is open. This is one of the reasons that I can point to that we mathematicians often have trouble with English. You is. Okay, so we want to show you. So how am I going to show? I'm hopeful that I can just do this directly. I don't have to be innovative. That's what I'm hoping. Okay. So how do I show? Evan, how would I show that U is open? I got to show every one of its points is an. That's right. That's what my goal. That's what the requirement is. If I can do that, I got it. How does Evan know that? He knows the definition. Is that okay? It wasn't something he's going to figure out. You've got to know that definition. Does that make sense? I'm not going to figure out how to say in Chinese, I want $1 million. Somebody's going to have to tell me. Does that make sense? So we're being told the definition. All right, anyway. Let T be an element of U. We want to show T in it is an interior point of U. Okay. How do I show something's an interior point? That means I got to show that it has a neighborhood that's totally contained in U. That's what it means. Okay, that's what I got to do. Okay, great. So that means, what that means is, since, I think it's going to work very similar to what we did. Since T is an element of U, then I can take where T is not. T is not an element of U complement. Okay, what do I know about U complement? It's closed. Since U complement is closed, it contains all of its limit points. Well, it doesn't contain T. And if it doesn't contain T and it contains all of its limit points, then T is not a limit point. Of U complement. What's it mean not to be a limit point of U complement? What does it mean to be a limit point for U complement? What does it mean to be a limit point for U complement? It means every neighborhood of T intersects U complement at some point that isn't T. Well, that didn't happen. So let me write this up real carefully. It is not true that every neighborhood of T will intersect U complement at some point other than T. Okay, Travis, what does it mean that not every neighborhood will do this? Not everybody is going to be 17 feet tall. What's that mean? That means there must be, what does that mean? Somebody has got to be,
One person's not.
at least one person's not. Is that okay? So that means, to say that it's not true that every neighborhood does this, that means there's got to exist one. Okay. So there exists a neighborhood of T say N sub RT. So this particular one. So there's one that will only that intersects U complement at possibly, I should say this, at possibly only. So it doesn't intersect it anywhere that isn't T. So it may intersect possibly at. Okay, if you give me something that isn't T, it isn't going to intersect. It isn't going to be in both of them, both the neighborhood and U complement. What's the only thing that could be in both? At some point other than T. But T might be in both. Is that okay? So T might be in both. Is that okay? And only. Possibly. I guess possibly is good. Possibly only. So one place that they might intersect is at T. But wait a minute. T is not in U complement. Is that okay? But T is not in U complement. So you say, well, maybe they intersect at T, but they can't because T isn't in U complement. Is that okay? So what does that say about this set? This set doesn't intersect U complement. But there was some issue. We're saying, hey, it doesn't intersect U complement at any point that isn't T. That's what we're saying. Well, could it intersect at T? No, because T is not in U complement. But that's something to consider, okay? So nRT intersect U complement equals to the empty set. Is that okay? Well, where does that mean that this neighborhood is? Where is this neighborhood? If it doesn't intersect U, it's got to be containing, we'd say a subset of U. Is that okay? Oh, great. I'm glad I wrote all this down. Here, so, voila. So what does that say about this neighborhood? We just said it's all contained in U. Okay, now this is a neighborhood of T. Is that okay? So what did we just see? What did we just produce? We produced a neighborhood of T that was contained in U. What's that mean? That's right. Is that okay with everybody? And what does that mean? That means we took an arbitrary element of U, and what was it? It was an interior point. So U is, because everything in U is an interior point. We got a few more minutes. Okay? I want to do one more proof, and this is one that I had mentioned to Christy about having pictures with it, but I'm going to go on to it in just a second. Travis, are we all right? Okay, here's the one I want to do. I think one of the things. Let's do this last one. Where's that sheet of paper? Here it is. Here's what I want to show you. Got a picture. Statement. Here's its theorem. If K is a compact subset of a metric space, then K is closed. Then we're going to call it. I'm going to have office hours for an hour, and I'm going to come in to tape. So I hope to have video lecture 17 up later tonight. It'll be the last thing that'll be for the test, I think. I think I'll cover chapter 2 before this last thing. Proof. Let K be a compact set, a compact subset of a metric space. X. We want to show K is closed. That's beautiful handwriting. Sometimes beauty's in the eye. Okay, what I want to tell you is that I want to show you K is closed. And so what we've been harping on is that definition. What does it mean for K to be closed? That it contains all of its limit. But that's not the only way to show something's closed. We can also, we have a fact, I didn't prove it today, but it's a corollary of something we did today. We have a fact in our course that a set is closed if and only if its complement is open. So that gives me two means by which to try to prove this. Does that make sense? If I can show K contains all its limit points, we got it. If I can show that the complement of K is open, we got it. Does that make sense? Okay. Look, we've done the proof. And if we study it, we'll see that it does it one of those two ways. I mean, there might be other ways to do it. But it works on, I believe, if my memory is correct, is that it works on showing that K complement is open. That's what it works on, okay? So that's what I'm going to try to do. I'm going to try to reproduce that. So I'm going to remember that part, actually. Hey, I'm going to show them K complement is open. I think I can do that.
Dr. Whitaker,
Sir?
did you say that K will be closed if and only then?
K complement is open. Yeah, that's a fact. Yes, sir. I sure did. That clock's wrong. It doesn't matter what time it says. Show K complements open. Okay, so let P be an element of K complement. What I'm thinking is that I want to show it's an. That's exactly right. I want to show it's an interior point. I hadn't shown it. That's what I want to do. So here's what I'm going to do. Aaron, I'm going to draw here to the side picture. There's my message space. Here's K. I'm looking at something over here. Put it right here. That's the point B. That's what I got. So what I'm going to say is, for each Q element of K, so I'm going to take something in K. I'm going to draw a picture in just a minute, Christy. Okay? For each Q element of K, consider the neighborhoods. Okay, so I'm going to call it V sub Q comma P of P and W sub Q is the neighborhood of Q. Each having radius less than the distance between P and Q. So I'm going to look at those sets, okay? So they're kind of like having pairings of neighborhoods. And that's what I'm looking at. So I'm going to draw a picture. Just a second.
Give it back.
A chance.
Where is this supposed to say W sub Q comma P or just W?
W sub Q, that's what I'm going to leave.
Yes, sir.
Okay, so here's what I'm doing. Angie, it says for each Q in K, there's a Q in K, right there, there's one. And he says, look, you look at the neighborhood take a neighborhood about this guy and a corresponding neighborhood about this guy, such that their radius is less than half the distance between them. So that means that B is less than, oh, it should, half. I made a mistake. Thank you. And the reason we're going to pick half is if I pick a radius that's half the distance between them, when I look at those neighborhoods, they're not going to intersect, overlap. So, you know, less than a half. Maybe it's this guy and this guy. Is that okay? Those two correspond. But I'm not going to do that just for this Q. I'm going to do it for every Q in K. So what I'm going to do, I'm going to do it for this one over here. So this guy, and this guy another, we call it V sub Q sub P. Maybe it's this guy. It's a different one than what we just had. Is that okay? So I'm going to have a bunch of pairings. Does that make sense? But I'm going to tell you, I keep doing it over here. I keep doing it over here. I keep doing it over here. You know what I'm forming over here? Yeah, a collection of open neighborhoods, right? Neighborhoods are open. So wait a minute. So it says, look at that collection over here. Now note, now what were they? Those were neighborhoods of Q. That's what I'm calling W sub Q. Okay? Note, and here's the way I would write this, Don. Note that the collection of the W sub Q's, okay, here, how am I indexing? I'm indexing them with Q. What's the indexing set? Where's Q?
Okay.
Yeah, K is the indexing set. So we got, for every Q in K, we got a W sub Q. Oh, that's a lot of them. Okay. Uncountably many, maybe. I don't know. What this guy is an open cover. It's a bunch of open sets. 4K. Is that okay with everybody? Open cover. Man, I got uncountably many circles over there. Can't count them all. Okay? K is going to be in the union of them. They're all open. K is. What kind of quality does K have? It's compact. And so, all of a sudden, because it's compact, every open cover has a finite subcover. So I don't have to have uncountably many of these balls over here. I'm only going to have finitely many. I only got a few. Since K is compact. Then there exists a finite subcover. Of K from this collections of WQs. We're going to call it quits in just a minute, okay? I'm going to go just a little over. I really don't care. I'm finishing. Okay, let's call them. So W sub Q1, W sub Q2, so these ones I need. All the way up to W sub Qn. That's the ones I need.
Those are subcovers?
They are open sets. They are contained. They are part of this this covering.
Open covers.
So they form an open covering of K. Okay.
And they are neighborhoods.
And they're neighborhoods. So that's what makes them. That's exactly right. Good for you. Okay, that's where we are. So here's your snapshot, everybody. He's not here. That's what we did. So we only have to look at some of these W's and Q's. So instead of having uncountably many of them maybe over here, we only got finite we have to worry about. And for each one of those finite ones we got over here, we got a corresponding neighborhood of P. Okay. So then, let's look at those guys. Yeah, that's fine. I know you see me do this in the tape. Every once in a while you see me go. I'm just making sure I'm not off the board. It isn't because I can't find the board or something. I don't know what you guys think. Who knows?
Dr. Whitaker,
Sir?
does it matter in the picture, and this may be irrelevant, if they're open?
Did I included the border or something like that?
Is,
Nah, I mean, well, I should have drawn with dash lines, but I got excited. Maybe be consistent. That's what happened. Yes, sir. That's what our Richard. That's what we normally do. Okay, so then, if you look at, we have the corresponding V sub Q1 P P, V sub Q2 P, all the way up to V sub Q, what do I call it, N? P, which are our neighborhoods of P. Okay. So what I'm going to do is, let's notice this. Note, K is, I know I went back here, K is contained in this union. As maybe I runs from 1 to N of the W sub Qi. You union up all of these guys, K is contained in there. Okay, because that was a finite subcover with K. Okay? Now, the intersection of the V sub Qi, P, look at those guys. As I runs from 1 to P. That guy, first of all, is a finite intersection of what kind of sets? Open. And a finite intersection of open sets is open. You might have an uncountable, or you might have an arbitrary intersection of open sets. They may not be open. Arbitrary unions of open sets are open. We proved that today. Okay? The finite intersections of open sets are open. We can say that. If we extend to intersections of more than finite sets, they may not be open. It has some problems. Okay? Okay, this is open. It's open. And what can you tell me? I'll tell you this. This intersection, I don't know what I wrote here, this is wrong, what should it have been?
And
Yeah, sure it should have. Good. This intersected between the union of the intersected of the WQIs. What's that equal to? Yeah, I sure can. So think about, if you just take these finite ones and you intersect all these guys, you union up all these guys,
An offset.
it's an offset. And the reason it can't have any intersection is because pairwise they don't have any intersection. Is that okay? So here's what you think. Hey, look, if you're in here, if you're in here, you're a point in here, you got to be in one of the WQ sub i's. Is that okay? You're in one of them. If you're in that one, you're not in the corresponding V. And to be in the intersection, you got to be in all. If you got to be in this intersection, the intersection here, you got to be in all. And so you said both. You got to be in both of these, but you're not in this one. If you're in this one. Okay. All right. So that's what we have. Okay. So that's the empty set. So here's what I've done. I've got finitely many guys over here and one open set over here that don't have any intersection. Is that okay? You union up all these finitely many guys, you get K. This guy doesn't hit that guy. So that means, what about these, this finite intersection? Well, it's open. Okay? Since this guy, we're almost done. I'm going to call it quits for 3 minutes. Since this intersection, what do I call it? B sub Q I P is open, and P's in it, and contains P. What's that mean? Well, it means that P is an interior point of this. I'm going to skip that. What does it mean to be an interior point? I'm not going to write that down. Of this intersection. Okay. So, there exists a neighborhood of P such that that neighborhood is totally contained in this intersection. And what do we know about this intersection? It doesn't have any intersection with these unions, right?
Right.
And this union covers K. So it can't intersect K. So that means that this guy here has to be contained in, if it's not in K, it's got to be contained in. Okay, so what just happened? P was in K complement. I just found a neighborhood of that point that's totally contained in K complement. What does that mean about that point? I don't know. I'm trying to make you feel better. I don't know if it makes you feel better or not. And so what does that tell me about K complement?
It's open.
And what does that tell me about K?
It's closed.
And that's what we're trying to show. And that was the picture, Aaron, that was going along with it. I didn't write down the picture, Christy. Okay? I didn't write, but that's it. So, in some sense, what is your teacher expecting you to do? Make this picture on your own? I think that'd be kind of good if you could, but I think it's kind of tough, Tiffany, for somebody to do that. Okay? But that's what's going on here. Okay? You get what you can. We're hopeful it's enough. We're going to show a lot of material. Ask yourself, why is that line true? You true stuff? All right, that's more than my time, so we're going to call it quits there. I thank you very much for your time and patience.